Hello everyone. Today I have a special video because this is not about the MMORPG we are building. This is about a small project that I have with a friend of mine where we are building a Steam game with tower defense mix and a factory builder mix. For factory building I really looked into Dyson Sphere and was really impressed that it was made with Unity, and I was wondering how they could render so many objects with Unity. Maybe they were using ECS or the job system, but it didn't felt that way, to be honest. And I found this great function which enables you to render a lot of objects on the screen without any problems, but I wanted to have it work with shader graphs so I can write my custom shaders and rendering with it easily, and a quick Google search said that shader graph isn't capable of doing that, but I managed to make it working. And this is what I want to show you. Let me first show you the issue that we have. I have a small scene which is just an empty universal render pipeline scene with a little spawner script on it. Let's check out the spawner script, which is just spawning some amount of items with a prefab. Our prefab is just the default cube of Unity, so it's doing pretty much nothing, and we have 100,000 of those. So when we have 100,000 of those cubes, they will all spawn and they will all be rendered within each other, which shouldn't make a difference. Then we have a lot of trouble with Unity handling 100,000 objects. I could also remove the collider, which shouldn't do too much. Still, rendering will be an issue, as you can see here. The problem is that we have 100,000 game objects. So I built a factory game where you have a lot of belts and items on those belts traveling around. I don't need game object features of those belts, to be honest. I just need them to be rendered. So I have basically a belt management system which just pumps out to the graphics card where the belts and which items are on the belt, and the graphic card should render it. I don't need each belt to have specific logic, because to have this scale of logic, it's better not to run those in GameObject, because GameObject are classes, and if I have 100 million classes with just switching items on the belt, it's way more efficient to have a struct or just an array and move the items in this array, which is what this will be at the end. But we want to focus on rendering this, because shader graph is not capable of doing that. They said they will implement that in the future, but I still want to go with the LTS version of Unity. So that's why I don't want to update to beta to test this around. But I will show you how to make this work in the LTS version. So first of all, let me put up this scene and show you what I promised. I have a renderer and I promised 1 million items, but then we don't have no items on our belt. So this will render 1 million belts with no problem. So we have 1 million belts on the screen, and as you can see, it's running at 60 FPS. Those spikes is basically debugging, so if I make a release version out of it, we have 60 FPS without any problems with 1 million objects. And those objects are even animated with shader graph, basically a scrolling texture. So how do we do that? There is a function which is simply called DrawMeshInstancedIndirect, which uploads the mesh, the material we want to use, some bounds. I just made them really big so they are always within the camera frustum. Then we have our compute buffer, which is basically the core trick how we can define for the shader what each item, where it is in location, rotation, and some metadata like color and everything. We can put everything in here which would be unique per instance rendering. And then we have no submeshes, that's why submesh is 0, and we have no arcs offset because you can make an efficient array and have pumped to the graphic cards multiple offsets, so our offset is 0. Then we have a material property block. To be honest, I don't know what this is needed for, but I give it an empty one, and I created one for each rendering call and it's working, so I suggest you do that too. Then we can configure if they cast shadows and if they receive shadows. This function call needs a specific feature in the shader, which shader graph doesn't support. Let's look at our shader graph shader really fast to understand what is happening here. First of all, we get the object position. This is a little trick because we don't, those two shader graph nodes basically do nothing. But I want to have them executed in the vertex shader. So this object position is just passed through this object position. Those two nodes basically do nothing. But if we check the first node in shader graph, I've configured the vector 3 in, so I can put the object position in and the vector 3 out, so it passes it through. And if you look at the code for it, it's out equals in, so out equals in. What comes in just goes out. But I hack in a pragma instancing option for the shader. And this code looks like this. It's really small in the video, but I will put a link in the description with a GitHub link where you can download the project for free and test it out and play around with it. So it has pragma, instance options, procedural, and then instancing setup. This calls a function within our shader for setting up the world matrix and the inverse, the object world and the world object matrix, or the world matrix and the inverse world matrix. That's what we want to configure per each object. And this function basically is just hacking in our whole shader script. So this is referencing a file with the function instancing. So this is the file, and let's look at the file. The file is really short. We have an if not defined bell shader included, defined bell shader included, so that I can reference this file multiple times and it will just execute it once per compiler run through, which is exactly what we want. We defined our structure of our instance data. Our structure is just the world matrix and the world inverse matrix. And then we have basically our material has a variable underscore per instance data, and it has the structured buffer of our instant data. Then we have our instancing setup, which just sets the world matrix and the inverse world matrix by the one we pre-calculated with our instance data. This function is called per each object that we want to render because of this pragma instancing object. This name instancing setup needs to match this name. So Unity now in the vertex shader sets the world and inverse world matrix based on the data we give it per object. And now we have this instancing function which calls instancing underscore float, which is this function. And as you can see, it's basically like the other one. It's in comes position and out goes the same position. So it's basically doing nothing. It's just for us to hack in this code into the shader graph compiled shader. So then we have everything set up. The Shader Graph knows our shader file, and Shader Graph knows how to do our instancing. There's only one thing to miss. We need to add the keyword procedural instancing on for Unity to know that we have an instancing shader. Definition needs to be multi-compile and scope needs to be global, and we default them. We don't need to expose it because it should be always true, else this is not working. But for good measures we expose it. So everything's set up. Now the object should render fine. But obviously it has the base color. So when I change that and I just render belts, which I do, then we will see that it just has the basically gray boxes rendered, but they are all in the right position because we are leveraging the instancing data we give the material, which we will look into just now. The only thing I just added also was I added a time node, multiplied it by a speed value, and put it into a tiling offset, which basically offsets our UV coordinates, have an arrow texture, and just let the arrow texture move around. Then everything where the arrow texture is transparent, I set a fixed color as background color for the belt. So I have the arrow and everything transparent is basically our fill color, and I put that in emission and base. So put that in both so that I can use HDR colors to have some glow and bloom effects. So when we check out the belt material real fast, we have this arrow, we have a speed of -1, and then we have this color, and we need to do instancing on. So for example, I could make them maybe pink and let them glow. Then we should see around the belts a pink color, around the arrows a pink color, and it glows like madness. So this basically sets you up to render easily 1 million objects with the shader graph. Let me put back a normal color. So let's check how the instancing data is created. That's really simple. We have our compute buffer, and we have a struct for the compute buffer. In our case, it has a matrix and an inverse matrix. And then we need to define how big is it in bytes. It's really simple. We have basically 16 bytes per matrix because it's a 4 multiplied by 4 matrix. So we have a size of float 4 multiplied by 4, and we have that 2 times for matrix and for inverse matrix. I also added another feature to have multiple on this running. I have items which are on the belt, which also have instance data, but they also have a third parameter, which is color, just to show that there could be per rendering a different value. It's not just the matrices you can do basically everything you want to use in your shader here. So when the object is enabled, we instance those material property blocks for the items and for the belts. I initialize the bounds to be really big, and then we have an initialized buffer. This initialized buffer just calculates, because I have X and Z coordinates in my case, but in 2D you can say X and Y. I get the square root of the count, and then it will produce as many on X as it will produce on Z or Y. So we have amount per line is basically the square root of count, and the amount of lines is also the square root of count. So lines multiplied by amount per line should match the count, basically, if the count is a proper square root, which for the values 1000 10,000 and something. For 10,000 it's 100, because 100 multiplied with 100 is 10,000. So we have our instance data, which is the belts in our case, and we have a list of item data, which is our items on the belt. This is a list because I don't know the size of it. It would be way more efficient to have an array and do pooling that way, but for easy sample code I made it this way. So we go through for each x in line, we create random values for our item. First of all, we create a random value between 0 and 1, and if this value is below or equal what the chances of a belt line to have an item, then it has an item or it hasn't an item. Then we do a random check, do we want item 1 or item 2 on the belt, and then we assign some random value with some HDR intensity between 1 and 8. This is per line, and all items will be on one line. And then per item or per belt on the line, we create an instance data, which is just a position, a rotation, and a scale for us. As a mesh, I use the default cube, so I squish it really small in the y-axis to have just basically a sprite or just a really thin cube. And then we create with matrix for x4.transform rotation scale, we create the transform rotation scale matrix for our object, which is basically where is our object, how is it scaled, and how is it rotated. And for matrix inverse, it's just the inverse matrix. And this is everything our current belt object has in the data. And this is done for all of these 1 million belts. Then if the belt has an item, we basically do the same thing for the item. It has a position, it has a rotation, it has a scale, and in our case it has this item color also. And then we add those items to item 1 or item 2 depending on what was selected. At the end we need to get a compute buffer, which is often called args buffer. Which should be get args buffer is a way better name for that, because the args is always like that. We have the mesh index, the amount of objects we want to render, and then in most code I have seen it's 0, 0 here, but for us it's how many meshes, how many objects do we want to render, where does the meshes start if you have sub meshes, and where's the base vertex. If you have a simple normal mesh, this is 0, 0, and the index count is 1, because we have, or it's also 0 most of the time. But this is the full configuration for the other one. This one should work for all meshes. Then we generate a compute buffer out of it. We set the data. We just have 5 values with the size of uint, and it's an indirect arguments. We return this buffer just because this buffer is always created the same way, we put it in its own function. And then we have our instances buffer, which is basically a compute buffer with our instance data in it. It's this instance data or this item instance data. And we put this instance data, we write it in it, and then for the material we do set the buffer underscore per instance data. And if we look into the shader again, this matches this name, so it sets in the material the structured buffer to our instance data. And then we just have to do our rendering call with our mesh, with the material, the bounds, the compute buffer, and that's it. The compute buffer is the args buffer. Let me rename that real fast. Sorry for that. So we have our rendering call that makes more sense, because when you look at this call, you see that this, we have the mesh, we have the submesh index, which is 0 because we have no submeshes. We have our material, our bounds, and our arcs buffer. And the rest we don't need to give it, but we can. Material block property, shadowing, and receive. In our arcs buffer, it is basically the count, how many objects will be rendered. And in our material, we set it the destructured buffer in the material. So the arcs buffer tells the graphics card how many are they, and in the material is the data already stored when it's pushed to the graphics card. And that's basically how you can render that. When we want to render those with items, we definitely need to do not 1 million, because if I do more than 1 million, we might have rendering issues. This can't render. On my machine, 1 million is basically the limit. So 50% chance to have for a line to have an item now, and we have belt material, item material. And as you can see, then we have basically items on 50% of the belts, and still the profiler is pretty happy with that. Let's really end this video with looking into the shader of the item one, because the item one also has this property for the color. So I do the same like I did with the arrow. I get the texture, which for item 1 is gray and for item 2 is red. So if we check here, we have those with the gray circle in it, it's item 1, and those with the red circle is item 2. And what we just take the texture, which is the circle in our case, and like we do with the other one where it's transparent, we add the color, and where it's not transparent, we render the texture. And this color is referencing also our shader file with the function getColorItem. If we look at the shader file, we have two. One is the one for the belt and one for the item. And the one for the item has in its structured data the float for the color. We need that. And then we add this getColorItem_float function, because in shader graph I said the name of the function is getColorItem, and shader graph will add an _float because it's working with float values. And we have an output of a vector 4. So this gives a color or a vector 4. In the case of shader graph preview, we will return just white. But if it's not shader graph preview and we have instancing enabled, which should be always the case because this is not working anyway if instancing is not enabled, then we will return our per instance data with the Unity instance ID and the color of that instance ID. We also have a function to get this instance ID. This is often used when you want to do randomization or something in your shader graph shader. But we get the color this way. And for each property you add here, you want to add a function like that, and then you will be able to do it in shader graph with the custom node. These nodes are added like right click, create node, custom node function. Then you have to configure inputs and outputs. Let's say we want to do the get color one. Then this is a vector 4 we want to put out. We select our file and then get color item, I guess is the function name. And then this will turn like this one. Then we could also give the output a name. It's a color. And then we have this node with our shader file reference. For those at the top here, this is basically the same. We do create custom node. We have here in is a vector 3 and out is also vector 3. Sorry, I didn't click the correct node. We name this out, we name this in for the input. Then this is a string, and let's copy this over. We give it a name, can be dummy, can be anything. Then we can hook this up instead of the other one. And it should still work totally fine. The same happens for this one. We have a custom node. Our in is again a vector 3. It's named position, because in the shader I named the variable position. We have out as out. We reference our shader file in this case. It's the item one. And then it's instancing item. Then we reference that. Let's remove that one. And let's check if everything is still working. So we have some errors here, which we already fixed. But it shows the errors because there were for shader compilation. It shows the errors and doesn't remove it. But when you clear it and you click on the shader and you have no errors here, then everything is fine. Let me show you how some of the errors look like so that you get an idea. Let's say you forgot the dummy function. Then you will get a very specific error. You will get the error Unity instancing procedural func must be defined. Because you have procedural instancing on, the default Unity shader wants to have a function that it needs to instance to. And you didn't provide that, so you get this error. For example, if we have the naming here wrong, then this will say instancing item 2 underscore float is not available. This is how you find out how your function needs to be named in the shader. But with that, the shader is working again. Let's give it a try. And then this is how you can render a lot of objects with that obviously don't have per object logic, but you can easily write a manager for that, which moves the object around and just saves the data in your compute buffer and give it your graphics card to render. This is a very, very efficient way to render graphics in Unity with shader graph. This is everything I have today. I want to thank you, my patron Julian, for the big support in this project. If you have any questions, please leave a comment, subscribe and like to the video, and I wish you all a great weekend. Bye.